All right. Good morning, folks. Happy Wednesday. We're going to go ahead and get started with 11.4 today. And so 11.4 is about something called alternating series. But to begin our lesson, we're going to spend the first part of it sort of reviewing our special series and the tests that we learned yesterday, just so we can kind of feel maybe a little bit more understanding of those tests and when to use them and how to know when to use what. And so that's where we're going to start, and then we'll finish the class with the alternating series, which I think is definitely more along the special cases, but we can't find sums necessarily for them. But it is a very clear situation when it is an alternating series. Okay. So that's where we're going to get started. So I'm going to go ahead and share my screen. All right. So section 11.4 is called alternating series. And so what we know so far, we know the divergence test, we know the integral test, we know the basic comparison test, and the limit comparison test. And we know that some of them tell us more information than others. So of these four, which one do we think gives us the least amount of information?
The divergence test?
Yeah, the divergence one, right? Because it only tells you whether if it diverges, but it doesn't tell you for sure if it converges or not. And so in that sense, it's one of the easier tests to do, but it doesn't always give you a lot of information. And then we talked about the integral test yesterday. Can someone maybe summarize for us when a good time to use the integral test might be?
In case it's positive and decreasing?
Positive and decreasing, yep. So we have to check for those situations. But when we look at our a sub n, how do we know, oh, maybe we could use the integral test?
If it's easy to integrate?
Yeah, if it's easy to integrate, right? If you've got like a 1 over n or like a n squared or just anything where it's not too bad to integrate, that's definitely a good chance to use the integral test, okay? But we do want to make sure that we check that it's positive and decreasing before we do that. All right, so then at the end of yesterday, we talked about the basic comparison test and the limit comparison test. And the basic comparison test, I think, was a good introduction to this idea of why we need to know our special series. And we were able to use it to compare something that looks very complicated and then sort of strip away different parts of it so we could get it to look like something we already know. What were some limitations of the basic comparison test?
I believe that if the large one converges, then the smaller one converges, but it doesn't go the other way, and vice versa. If the smaller one diverges, then the larger one diverges, but if the larger one diverges, it does not go the other way.
Right, or we don't know. So in some sense, what James said is correct, right? So that's just maybe like some sentences that we want to get down on that cheat sheet for tomorrow. But when we think about the basic comparison test, to me, sometimes it feels a little like the divergence test because certain parameters have to be true in order for it to tell us information. Otherwise, it might be a little inconclusive and we'd have to try another test, okay? Can I get someone else to tell me a little bit about the limit comparison test?
So I think that for the limit comparison test, we choose B sub n, which is something that we do know to tell if it's diverge or converge. And then we're just gonna multiply the conjugate of that by the series that we have. And we will see that's gonna tell us if it's acting the same as the B sub n or not.
Mm-hmm. Yeah, so that's a really great summary. Maybe just one thing I want to clarify on that one is that we're not necessarily looking for the conjugate, but we're looking for the reciprocal, right? We're looking for that 1 over to multiply our a sub n and our b sub n.
Oh, sorry, I thought that conjugate is that, like the 1 over that.
You're totally fine. I know what you meant. Okay. So those are some of the tests that we learned yesterday, right? In addition to the special series that we learned on Monday, where we had a geometric one, we had a telescoping one, and we had our P-series, or the special case of the P-series, which is the harmonic series. And so what's new today, after we review a few of those other ones, is we're going to take a look at something called the alternating series test, okay? And so what we've done so far is all of the terms, all of the tests we've looked at have dealt specifically with positive terms or overall positive terms. But in this test, we're going to start to look at what happens if we have positive and negative terms in the same series. Okay, so we have positive and we have negative terms in the same series. And so that's going to be sort of the new part for us today. Okay. But before we get there, let's take a look at some of our special series tests. Okay. So we've got 3 questions right here, example 1, example 2, example 3. And I'd like to give you a few moments to see if you can determine whether each one converges or diverges. And if it converges, and it's possible to easily find the sum, then find the sum, okay? So only if it's easy to find the sum, find the sum. Otherwise, just tell me that it converges, okay? So take a moment, warm up those brains a little bit, and work through examples 1, 2, and 3, and we'll check in about 3 or 4 minutes, okay? All right, if you are done, maybe just type done into the chat. If you need a couple more minutes, maybe type in like 1 if you need 1 more minute, 2 if you need 2 more minutes. All right, let's split the difference there. Maybe let's take 1 more minute and then we'll start sharing out some answers here. All right, so let's start with example number 1 over here. We've got this infinite sum of 1 over n to the pi. Can I get someone to share out whether this converges or diverges and give me some reasoning as to why you know it does one or the other?
Converges.
All right, so you say this one converges and your reasoning?
It's a p-series where p is pi, which is greater than 1.
P-series, p equals pi, which is greater than 1. Excellent. All right, so now this one, these are not necessarily easy to find the sums of, so we're just going to leave this one the way it is. Okay, so we say it converges, we've got the p-series, p equals pi, which is greater than 1. Perfect. Okay, are there any questions about example number 1?
Yes, I do have a question.
For sure. What's up?
I thought that if I will do the limit goes to infinity, then I can find the sum of it.
That gives you the last term, because this right here, this is an equation for a sub n. This only tells you what each individual term is.
Oh, okay, yeah. Thank
Okay.
you. Yeah.
Okay. All right. Any other questions about example number 1? All right. What about for example number 2? What do we think? Converging, diverging, and how do we know?
It converges because it's a geometric series and r is less than 1.
All right, so geometric series, I buy that because we've got sort of this 7 something to a power. Our r value is less than 1, okay? And when we have this r value and with the geometric series, we can actually find the sum. So how do we set up to find the sum for this geometric series?
A sub 1 over 1 minus r.
Perfect. A sub 1 over 1 minus r. So our a sub 1 is going to be 7. And our 1 minus r is going to be 1 minus negative 2/3. Okay, so we do want to be a little careful there, kind of sneaky because that r value is negative. So we want to make sure it's like minus the negative. And so that'll give us 7 over 5/3, or 7 times 3/5. Or if we added up every single term in this series, we would get 21 over 5. Okay. So a good compare and contrast about how example 1 and example 2 both converge. We had to use different reasoning to determine whether they converged because they were different types of special series. But one of them we could find the sum for easily, and then the other one, it would just take, it's a little bit more complicated, okay? All right, we've got one last one here. We've got our example number 3, okay? So we have this infinite sum of 2 over n minus 2 over n plus 1. And so what do we have here? Is this one converging or diverging, and how do we know?
I'm going to say converges.
Okay, you're going to say that it converges, and tell me how you know.
It is a telescopic series.
Mm-hmm.
And when you sit there and just working it out, when you take the limit of it, you get an actual number after you sit there and you find your S of n.
Okay. So let's write out a few terms, right? So we've got this if we plug in 1. We've got this if we plug in 2. We've got this if we plug in 3. And we sort of keep going, and at the end, we could write a few of them. 2 over n minus 1 minus 2 over n plus 2 over n minus 2 over n plus 1. Okay. So James, I really like the way you described that, because in this setup piece, right, a lot of things cancel out. And so we are left with just the first term and the last term here. So we have 2, and then we have this minus 2 over n plus 1. But what James said, in case you didn't catch this, is that 2 minus 2 over n plus 1 is the infinite sum, okay? So that, in that way, it's a little bit different than some of the other ones where we just have our a sub n. In the telescoping series, we're actually able to find a formula for the sum, kind of like the geometric one. Okay, so the geometric formula is the same every time. The telescoping one, you do have to work through it and find out what it is. But once you have this, if you take the limit of s sub n as it goes to infinity, that does give you the sum, okay? And so we'll get 2 minus 2 over infinity, which is 2 minus 0, which equals 2. Okay.
Professor, could we also have written it as a partial fraction and then, or is it, actually, never mind, it's already simplified.
Yeah, exactly. And so example number 3, because I didn't want to spend too much time today like reviewing these ones, but I could have asked example number 3 in a different way, right? I could have been in a place where you had to use partial fractions to get it to look like this, and then you could cross out all those terms. Okay, so that's actually a really important point to bring up. Sometimes it's this obvious, and sometimes we have to do a little bit of work using partial fractions to make it look like this.
So I have a question about number 3.
Yes.
We know that it's going to be converged just because we solve it and we get a number?
Correct.
Okay.
So not all telescoping series converge. A lot of the ones we have been looking at do converge, because I wanted to kind of show us this like cool thing where you could like cross out a bunch of terms. But you're right, not all of them do. And there's not really a way to tell in the beginning whether it is or not. You kind of have to work through and see what cancels. And then when you take the limit of that sum, if you get a number, then it converges, okay?
Can I ask one clarifying question on it? When you were coming up with the formula,
Yeah.
were you trying to get it to where you only had one term with your n on the bottom? Because I noticed that for that series you picked n minus 1, and which would go ahead and give you to where something before that canceled out, and then that 2 over n is going to cancel out with your first term right there. I was just trying to like clarify the pattern on how you chose that.
Oh, it wasn't really, I think it was just based off of our conversation the other day. I just wanted to show people more terms, but you don't have to write out that many.
Okay.
I'm not sure that I'm answering your question.
I think it's, so I'm just a little confused on how you know what terms to pick, like 2 over n minus 1 minus 2 over n in the parentheses.
Uh-huh.
It's, how did you know to pick those two? It's just the regular functions but switched.
Okay. So when I'm writing out a few terms, like I decided to write out like this is a sub 1, right? I plug in 1.
Right.
Right? This is a sub 2. This is a sub 3. And then I was like, well, that's kind of enough with numbers. Let me see what happens on the tail end. So this is a sub n minus 1. And this is a sub n.
Okay, yeah, that's the part that always gets me. It's like, how do I know to pick a sub n minus 1 or plus 1, whatever? But
Because you're working your way up to n. So what comes before n is n minus 1.
okay.
Okay.
Okay, so it would just always be a good general rule that you do A1, A2, A3, or just to see what numbers cancel out, and then you want to start with A of n minus 1 to A of n if nothing's canceling out. Then that's when you go to A of n plus 1. Or typically you never get to A of n plus 1 because you want to end at A of n.
I think there's not really a general rule. So, like, I've taken classes recently where maybe some of my fellow students are, I would say, a lot better at finding out the patterns than maybe I feel like I am. And so I tend to write out more terms because when I write out more, I'm like, oh, I can kind of see what's happening. But there are some people who literally write like maybe a sub 1 and a sub n, and they're like, oh, I got it. I know what's going to happen. So there's no real like set rule on how many you have to write. So like if you didn't write the a sub n minus 1, it wouldn't be wrong as long as you kind of know, okay, this is the pattern here. I think I was just trying to, I think I confused you all and just trying to maybe write out more terms just so we could see like where things cancel out from. But like you don't have to write out a certain number of terms.
So is there no one set general equation for the thing? Like when it comes to the 2 over n plus 1 terms, like you can have like different equations just as long as your numbers are correct.
Well, like this term you mean?
Yeah.
Well, that term is when I plug in n into here. Like that's just what comes out.
I know how you got that. I'm trying to like see your pattern on how you chose your a sub n's. But it's all right. We'll go ahead. We'll
Okay.
move on. I just need more exposure.
Okay. I'm sorry. I feel like I'm not really understanding the question, but that's okay. We can revisit it. Sometimes time away just helps us all understand things a little bit better. Okay, so with these three, I think my greater purpose, without trying to confuse anyone, was really to just say like, okay, we can know some special cases. So like, know that in the grand scheme of things, these three series are like really special cases. They don't happen a lot. There's so many series out there that maybe aren't as cut and dry, but this is just meant as sort of an introductory, like here's some basic ones and they'll get you pretty far, but like the reality is there's a lot of other kinds of patterns. A lot of those you learn about in discrete math, so that's pretty cool. You come back and take a look at like these different patterns that are happening. happening, but as it applies to maybe like computer programming or just like counting how many different variations of something you can have. So there's a lot of really cool applications of it. I think this is a challenging section because we're sort of setting the foundation for potentially when you take these future classes, what kind of patterns you're going to see, okay? But in general, your discrete teacher is usually pretty kind about like re-going over sequences and series. So, okay, so on that note, let's take a look at the general series tests. So the ones that we saw yesterday, okay? So those would be the divergence test, the integral test, the basic comparison test, and the limit comparison test, okay? So we're going to take a look at example number 4, all right? So we've got this infinite series of 1 over 2n plus 7, and all of that is raised to the 3rd power, okay? Now, you can choose a lot of the different tests, but when I look at this one, I'm like, well, I think the 2 that jump out to me are the integral test and maybe the comparison test, right? I could do the divergence test, but remember, if I get 0 out, it's inconclusive. So if I look at this, I don't think that it's diverging because I think that the terms are getting smaller and smaller and smaller as you go. Like the bigger the denominator, the smaller the fraction, right? So in looking at this particular a sub n, I don't think it's going to diverge, so I'm not going to waste my time with the divergence test, okay? So what we're going to do here is I'm going to show you the integral test with this, and then I'm going to show you the comparison test so that we can kind of see like how they do support each other in terms of their answers, but also use it as a way to review like how the different tests work, okay? And by review, I mean we just learned this yesterday, so I thought it was important for us to maybe kind of see it again. So let's start with the integral test and kind of see where that gets us. All right, so if I'm going to do the integral test, that means I'm going to take the integral from 2 to infinity of 1 over 2x plus 7 cubed dx. And so that is a throwback to chapter 10 where we're looking at our improper integrals, right? So we're going to take the limit as t approaches infinity from 2 to t of 1 over 2x plus 7 cubed dx. And when we're looking at integrating this, what rules are we thinking we might need?
U sub.
U sub, right? So let's do our u equals 2x plus 7. That means du equals 2 dx, or du over 2 equals dx. And so when we plug that in, we're going to get the limit as t approaches infinity with a 1/2, the integral from 2 to t of 1 over u cubed du. And so that's nice because all we need to do is use the power rule. So we'll take the limit as t approaches infinity of 1/2. And when I take that integral, I'm going to get negative 1 over 2 times, let's put the u back in, 2x plus 7 squared. And we're going to plug in t, and we're going to plug in 2. Okay. I'm going to go ahead and bunch up all my constants. So like this 1/2 and this negative 1/2, I'm going to pull out to the front. So it's going to be negative 1/4. The limit as t approaches infinity of 1 over 2t plus 7 squared minus 1 over 2 times 2 is 4 plus 7 is 11, so 11 squared. All right. Now, when we take t goes to infinity, what happens to the first term?
Zero.
Yeah, it's going to go to 0, right? Because that denominator is going to get super large. And so we'll end up with negative 1/4 times negative 1 over 121, which is a very small number, as in it's very close to 0, but we have 1 over 484. Okay. Now, the integrating part is maybe not so bad, but we have to also know how to interpret our results. So what does this 1 over 484 imply for our original series?
Converges.
Say that again?
Converges.
It converges. Okay, tell us why.
Because we got a finite number.
Okay, it has to be finite. What else does it have to be?
And positive.
Positive. All right, so finite and positive. Okay, so that really is the important takeaway here. This number, so 1 over 484, is finite and positive. That means that our series converges. Okay, so 1 over 484 is finite and it's positive. Therefore, our original series converges. Okay. Does anyone have any questions about the integral test? So the other one that I thought we could try is the basic comparison test, okay? So let's try the basic comparison test. Now, we do need to come up with a b sub n when we're looking at the basic comparison test, okay? So we want to think about what can we compare this to. So take a moment, think about what we might want to compare it to. And then when you're ready, you can share out some ideas.
Will it be correct to compare it to 1 over 2n to the third power?
Okay, so I hear one idea that maybe b sub n could be this. Okay. Are there any other ideas?
Could it be 1 over n cubed?
So maybe or 1 over n cubed. Okay. Are there any other ideas out there? Okay. I think that these two are probably the most popular choices for the b sub n. Okay. So I think this goes back to thinking yesterday in one of our last problems that we did with the basic comparison test. We had a tricky situation where we had like a number added to the numerator as well as the number added to the denominator. And while if we tried to strip away both of those numbers, it made our b sub n look really simple, but we weren't then sure which one was bigger than which one, right? And so we kind of had to backtrack a little bit and say, oh, let's try and see, like, if we only take away one of these numbers, is it easier for us to see the pattern? Okay, so let's kind of use these two choices to decide which one might be a better fit for our b sub n. So I know that I have 1 over 2n plus 7 cubed. And let's see if we compare that to 1 over 2n cubed. Okay. But let's also say we're going to take our original and we're going to compare it to 1 over n cubed. All right. So take a moment and compare those, each pair to itself, and then think about which one you're able to draw a conclusion from about whether one is larger than the other or one is smaller than the other. Okay. All right, what do we think here? Let's take a look at the one on the left first. Is there a definitive relationship that we can establish between 1 over 2n plus 7 cubed and 1 over 2n cubed?
The one
Yeah.
on the left is smaller than the one on the right?
The one on the left is smaller, good, because the denominator is bigger, right? So that's going to lead to a smaller one. So, okay, that pair works. Can we say something similar about the pair on the right?
Yes.
Okay.
Yeah, okay. So we could say that the one on the left is smaller because that denominator has like a times 2, and then you add 7, and then you cube it. So yeah, I would say in this case, either one could be an appropriate b sub n. Okay. So there, it's okay to have a different b sub n than someone else might choose, as long as you can confidently say, yes, this one is larger than this one. And the one that I said is larger converges or diverges or whatever it might be. Okay. So what can we say about 1 over 2n cubed? Converges, diverges?
It converges
It converges. And how do you know that, Leo?
because that 1 over 2n cubed is going to simplify to 1 over 8n cubed, which is still a p series, and then the p would be more than 1, therefore it converges.
Perfect. All right. So if you simplify it, like Leo said, you'll get 1 over 8n cubed, and then 3 is larger than 1, so that converges. Okay, good. And then I think this one is a little bit more clear, right? We don't have to do any simplification, but we know that it converges, and our p is equal to 3, which is greater than 1. All right. Now, if we loop back to what James said earlier when he was summarizing the basic comparison test, he said something like, if the larger series converges, then so does the smaller one. And then he also said, if the smaller one diverges, so does the larger one. Okay. So we managed to find a series to compare it to. The series that we picked, whether it was 1 over 2n cubed or 1 over n cubed, they were both definitely larger than our original one. And both of those options converge, therefore our original function also converges. Okay. So we compared them, we established a relationship, and we're able to draw a conclusion from that relationship. Okay. And the good news is our result from the integral test and our result from the basic comparison test tell us the same thing. Okay. All right. Are there any questions on example number 4?
So professor, we always look at the larger one, right?
Well, so the other statement is that if you compare them and the one that you know about is smaller than the one you're comparing it to, if that one diverges, so does the one you're comparing it to. So you're not always trying to find a larger one. Once you pick, and maybe I would actually think this way, once you pick your B sub n, I would actually write out whether it converges or not. If it converges, you want to make sure that one is larger than your original. But if you pick your B sub n and you're like, ooh, this one diverges, you want to make sure that one is smaller than the one you're comparing it to.
Okay.
Okay. Okay, great question, Carlos. And I actually just saw you have a question from earlier that I'll answer in just a second. If it was squared, could we expand it and look at it that way? I think that you could expand it. Sometimes it's helpful to expand, sometimes not so much. I think that if you're looking to, I feel like we're almost at an interesting juncture in math where it's usually better not to FOIL out unless you absolutely have to. Sometimes it's easier to see patterns that way. Okay, Carlos. And then for your other question, do you want us to write out the limit as n goes to infinity or draw arrows? I do want you to put the limit notation in there in the front, at least in the beginning of your improper integral. But yeah, you can kind of tell I'm getting a little lazy with the infinities. Are those the only possible options we could use for B sub n? What might some other options for B sub n be?
I was just asking generally,
Okay.
identify what we could use for B sub n, just because I'm having a little trouble identifying.
Yeah. So I would imagine like maybe looking at your A sub n and just starting to take away one layer at a time. And it's almost like you want to go order of operations, but backwards. And so like order of operations says like parentheses, exponents, multiplication, division, addition, subtraction. So like if we kind of think about what I forget who said 1 over 2n cubed, but what that individual did was kind of take away the addition and subtraction. Because if we have exponents involved, the addition and subtraction is probably going to matter a lot less than a multiplication or division or a power as we're going to infinity, right? So I would maybe try one layer at a time. Try looking for addition and subtraction that you can kind of get rid of. Does that give you a series that you know something about? And if it doesn't, maybe try the next layer, which is the multiplication or division. Is there any multiplication or division that I could strip away? And then now, does that get me closer to a geometric or a p-series?
Okay, that makes a lot of sense. Thank you.
Okay, good, because I just kind of made that up, so I hope that makes sense. Okay, yeah, I actually think that could work. So maybe try it layer by layer until you get to a point where you're comfortable. I feel like in this case, both of these were totally valid options, but you know, we were patient about it. We tried both to see if they both worked. Whereas yesterday we tried both and like one of them wasn't really helpful for us. So we kind of had to go with the other one. Okay. So let's move on to example number 5. And then I think we'll take a break before we actually get to, oh shoot, there's an example 6. We'll do example 5 and 6. We'll do example 5 and then we'll stop. Okay, so example 5. we've got an infinite series. We've got 2 to the n plus 1 over 3 to the n. And I'm going to say for this one, let's practice the limit comparison test. Okay. Now, usually, but not always, when you use the limit comparison test, you probably could also use the basic comparison test. But sometimes you'll find that finding that b sub n that is either bigger or smaller than your original is actually where you kind of get stuck, okay? So if you're feeling like, oh, I tried the basic comparison and it's not going so well, try the limit comparison, because sometimes that just, you pick your b sub n, but then it's a little bit easier to see, like, interpret your results, okay? Because there's just sort of like less things you have to make sure are happening. So our limit comparison test says that we need to find a b sub n, right? So we need to find a b sub n for the basic comparison as well as the limit comparison. And so let's use this idea of order of operations backwards. And so that would mean that maybe the first term we strip away is that plus 1, right? Because the addition at the end, I'm taking terms that are infinitely large and adding 1. And then the 1 is kind of negligible, okay? So if I strip away the 1, I get 2 to the n over 3 to the n. How else could I rewrite this?
2/3.
2/3, like just cancel out the n?
Yeah.
Yeah, that is illegal. We can't just cancel out the n's like that.
2/3
to the n?
What was that?
2/3 to the n?
Yeah, we could factor out that power. That would be okay. All right, but we can't just cancel out those powers. So what's the benefit of writing it the second way?
Common ratio.
When I write it the second way, it is more obvious to me that I have a converging geometric series, right? I've got my 2/3 to the power of n, it's converging. So I know something about that series. Now, if you're in a situation where you're like, okay, I found my b sub n, I feel confident with that, but I don't feel as confident saying, is this one bigger or smaller than my original function? This is where the limit comparison test comes in handy, okay? So the limit comparison test says it doesn't matter which one's bigger or smaller, but you can take the limit as n approaches infinity of your a sub n times 1 over b sub n. That's one option. Or you can say the limit as n approaches infinity of b sub n times 1 over a sub n. So when you're comparing them through that division, it doesn't matter which one is on the top and which one is on the bottom, okay? So I'm going to use this first one right here. And so I'm going to write the limit as n approaches infinity of 2 to the n plus 1 over 3 to the n times the reciprocal of b sub n, which is 3 to the n over 2 to the n. Now I'm writing it this way and not in my 2/3 to the n because this form is more useful for me here, whereas the 2/3 to the n would be a little bit less useful, okay? But what I can see from here is that this 3 to the n and this 3 to the n are going to reduce to 1. And so what that gives me is the limit as n approaches infinity of 2 to the n plus 1 over 2 to the n. Now, as you go to infinity, all right, let's use a little bit of intuition here. As you go to infinity, what is this series going to approach?
Infinite, or it's indeterminate form.
1. Yeah, it is going to give us an indeterminate form, right? If we plug in infinity, we'll get infinity over infinity. And that would mean that we would have to take the derivative, right? So we have infinity over infinity. So we apply L'Hopital's and we get, what's the derivative of 2 to the n?
2n ln 2.
Yeah, it's almost like e to the x, right? 2 to the n, well, we have to multiply by the natural log of 2. And then that 1, the derivative of 1 goes to 0. What do I get when I take the denominator derivative? Same thing. Okay. So overall, what is this series going to approach, or the sequence going to approach?
1.
It's going to approach 1. Okay. So L'Hopital's definitely is a lifesaver when we're looking at not just improper integrals, but in the sense of that chapter, but also in terms of sequences and series, it's very, very helpful. Okay. Now, there are some of us who maybe were like, okay, well, if I think about this, like sort of graphically or numerically, I can tell that like this 2 to the n totally overpowers the 1. Like as n gets to infinity, adding 1 is going to be like no big deal, which means I really have like 2 to the n over 2 to the n, which is getting us to the 1. Okay. So depending on like your future coursework, that might be sort of some reasoning that you can do to say like, okay, I could use L'Hopital's, or I can kind of see the end behavior is going to be this. All right. Now we get 1 out, but numbers as an answer mean a lot of different things depending on our given test. So in the context of the limit comparison test, what does this 1 mean?
I think it means it converges.
So if we have our limit comparison test,
Both
that,
series converge.
what's that?
Both series converge.
Both series converge, right? Because what makes that true? Like what values would make both of them converge?
1 is greater than 0.
Okay, so 1 has to be greater than 0. And so this is greater than 0. And that means that it follows the behavior of the one you compared it to, right? But if the one you compared it to diverged and you got a 1 out, how would your answer change?
It would mean they both diverge.
Yeah, it would mean that they both diverge, okay? So whatever it's important to establish early on, like what your B sub n does. That way you know at the end, okay, if I get a number, it means they do the same thing. All right. So I think this is a good time for us to kind of pause. All right. We have taken a look at sort of the last couple days of content. We still have one more example to work through. And then we'll go through the alternating series, which I think the alternating series test is maybe a little bit more simple than the limit comparison or the basic comparison. So don't feel stressed out that we haven't gotten to it yet and we're like halfway through class. Okay. So it is 10:20, almost 6. Let's be back here at 10:35. All right, let's be back here at 10:35. And then we'll take a look at that one last example of our general tests, and then we'll move on to what happens if we have some positive and negative numbers going on in our series. Okay. All right, folks, we're going to go ahead and pick up where we left off. So we're going to take a look at example 6, which is our last sort of review of the other general tests, and then we'll dive into alternating series. All right, so let's take a look at example number 6. We've got this infinite series of 2 over 3 plus 5n. Take a look at that, and then let's name a few of the tests that maybe come to mind for this particular one. All right, I see a basic comparison test here. Yeah, what do you want to compare that to?
One over n.
1 over n, okay. So we could use our basic comparison test. All right. And so that would mean you said b sub n could be 1 over n. What else could b sub n be?
Two over 5n.
Could do 2 over 5n. Yeah. Yeah, I would agree. I think that either one of these options could work. And then I know, Carlos, you also said the integral test. And yes, I agree. I think we could also do the integral test. So if we were to do the integral test, all right, that would mean we would have the integral from 0 to infinity of 2 over 5 plus 2x dx. And so what rule would we need to integrate this?
U sub.
We could use u sub, exactly. So we'd get u equals 5 plus 2x, du over 2 equals dx. Okay. So we could definitely use u sub for that. All right. So let's go back to the basic comparison test. Let's finish that one. Let's take a look at the integral test, do that one, and then maybe we'll try the limit comparison just to kind of see. All right. So our basic comparison. Yes.
Why the numbers in your integral are different from the number in question 6? Is that a mistake? Or that's
Sure
like
is. I don't know what I'm copying down. Sorry. How's that? Better?
Thank you.
Uh-huh. Okay, so let's go to this basic comparison test. So if we choose either 1 over n or 2 over 5n, does our b sub n converge or diverge?
Converge.
Diverge.
Yeah, they're both going to diverge. And why is that?
Harmonic.
They're harmonic. Good. So let's see if we can establish a clear relationship between our original and the 1 over n. And then let's also see if we can establish a clear relationship between 2 over 3 plus 5n and 2 over 5n. Okay, So take a moment, see if you can determine whether one is smaller than the other or larger than the other. But in this case, what are we hoping that we can show? Are we hoping to show that our b sub n is greater or smaller than our a sub n?
Definitely smaller.
Ooh, let's be careful here. Which one do we want it to be? If we know that our b sub n diverges, the only way the comparison test will tell us anything is if the one we know, the b sub n, is actually smaller than the one we're given.
Oh yeah.
Yeah. Okay.
But backwards. Like I was looking at the 2/3 plus 5n and comparing it to the other one. But
All right. So can we say anything definitive about either one of these pairs here?
Our b sub n is larger.
Yeah, I would say in this second pair over here, it's a little bit easier, at least for me to see, because the only difference is that +3, right? So I know that that one is larger. I'm not
same for that
sure
one.
how much we're able to say definitively about this one, the second pair. Okay. I think the second, or the first pair rather, is a little bit harder to determine which one is larger and which one's smaller. So maybe if we think about sort of this class strategy that we just try taking away one number at a time, I think that might help us be able to compare things a little bit better. But in this case, though, the one that we know is bigger and the one we know diverges, so we actually don't have a conclusive thing to take away from our basic comparison test, because in order for us to know that the other one diverges, 2/5 plus n would actually have to be smaller than 2/3 plus 5n. So in this case, I would actually say that the basic comparison test is inconclusive. Okay. So I'm actually really glad that we decided to try the basic comparison test, because I think it's important to see that sometimes it doesn't give you the information that you want, and that's okay. All right. Now, if we kind of take the integral test, let's go back to this integral test and see if we can figure out from our integral test what we get. And so if we do that, we get the limit as t approaches infinity of the integral from 0 to t of 2/3 plus 5x dx. And that's going to give me 1/5 after my u sub, the limit as t approaches infinity of, actually, let's make that 2/5. The integral of 1/u du. And that's going to give us 2/5 the natural log of 3 plus 5x. And we're going to plug in infinity and 0. And that's going to give us 2/5 natural log of infinity minus 2/5 natural log of 3. And we know that this goes to infinity. And so therefore we have a situation where at the end we get an infinity when we use the integral test. What does that mean?
diverges.
Okay, How do you know? Like, how would you know if it converged? Like, what would you have to get as an answer in order for it to converge?
A numerical number.
Yeah, exactly.
I
Okay.
have a quick question about this. When you're setting it up, like you set up limit of t as it approaches infinity, and then you put the integral symbol with 0 to t. Okay, thank you.
Sorry, I'm not really sure what I'm writing this morning. Apparently, I can't even read numbers, so.
That's all good. I was looking at the wrong question earlier.
Okay. Oh, I found my 8-legged spider friend yesterday. I ended up finding that spider. I thought it had disappeared, and then I went to open up my binder of all my math things, and it crawled out, and I was like, ah, it's a math-loving spider, but you know, now it's no longer, so. All right, so we have this integral test. It shows us that it diverges, okay? Now, in the event that you try the basic comparison test and it doesn't work, I wouldn't necessarily jump to the integral test next. I just wanted to do that one because I believe it was Carlos had suggested the integral test, and it does work for this one, okay? But if the basic comparison test doesn't get you anywhere, the limit comparison test is actually a very nice next step. And so if we were to do the limit comparison test for this one, the nice thing is that we've already established a b sub n. That's the nice thing about jumping from the basic comparison to the limit comparison. So we're going to choose our b sub n as this 2 over 5n. Okay, so the only thing we took away was that plus 3, because that was the one that gave us a very definitive relationship there, okay? So if we set that up, we'll get the limit as n approaches infinity of, let's keep a sub n times the reciprocal of b sub n. And from here, we can see that this 2 and that 2 reduce, and that we end up with the limit as n approaches infinity of 5n over 3 plus 5n. Now, you could use L'Hopital's here, right? You could also think as n approaches infinity, the 3 is going to become negligible. So really, you're looking at a 5n over 5n situation. So what value is that going to?
1.
It's going to 1. And 1 is greater than 0. What does that 1 mean?
Both series diverge.
Ah, okay. It means that it doesn't tell you, oh, it converges or it diverges. It tells you it does the same thing as the one that you're comparing it to. Okay, so this means that the behavior follows b sub n. B sub n in this case diverges. That means that our original one also diverges. Okay. So we've got our basic comparison test. Didn't really get us anywhere. That's okay. We've got our integral test, easily integratable. We just had to use a u sub and a natural log, and we found that it diverges there. But we're also able to use the limit comparison test here. And we just have to be really thoughtful about what does our answer mean. If you get a number out with different tests, then they mean different things, okay? So I hope this first part was helpful, talking about just sort of reviewing all the different series. I know that it's summer school and there's just really not a lot of forgiveness in terms of time and the amount of time that you have to absorb something. So I know we have an exam tomorrow and I know you have a quiz due on Friday, but I did want to sort of help you along with that thought process there, okay? So now let's learn about this last test that's going to be covered on tomorrow's exam. And so as we mentioned earlier, most of the series that we've looked at have had positive terms, or in the long run, they've had positive terms. But alternating series are actually a very special type of infinite series where the terms, it's not just that some of them are positive and some of them are negative, but specifically they alternate. So if a sub 1 is positive, a sub 2 is going to be negative. And then a sub 3 will be positive and a sub 4 will be negative. So we're always looking at the signs flip-flopping between the terms, okay? Now, usually these series are written in one of the following forms. So we could write it as -1 to the power of n times some series, b sub n. That's one way to write it. And then another way to write it is that maybe you have -1 to the n plus 1 as the power. And so the -1 to the n and this -1 to the n plus 1, those are the parts that make it alternate in sign, okay? So these create the alternating. You can think about it kind of like an on-off switch, right? Especially as you move into more applicable mathematics. And you really, one of the important things in sort of the technology we use these days is the ability to not just say, hey, let's start this process, but let's also stop the process, right? So positive or negative, or mostly like positive and 0, those kinds of situations create this on-off switch, okay? So what is the alternating series test? First of all, you can only use this when it's alternating. So if it's not an alternating series, you cannot use this test. But there's only 2 things that we need to check for, okay? We can say that if we take the limit as n approaches infinity of not the alternating part, but only the b sub n part. Okay, so if we take the limit as n approaches infinity of the b sub n part, and that equals 0, okay, that's going to be one thing we're looking for. The second thing that we're looking for is that our b sub n is a decreasing sequence. Okay. So if we can identify these 2 things about our b sub n, that means that the alternating series is convergent. Okay. So let's take a look at some examples. So number 7 is an alternating series, right? And I know that because I have a -1 to the power of n. So this part right here tells me that it's alternating. What does that mean the b sub n is in this case?
1 over n.
1 over n, good. So this is our b sub n, okay? So let's see what happens if we write out a few terms, okay? So we're not gonna graph this, but like let's write out a few terms and see what happens. So when I plug in 1, I'm gonna get -1. When I plug in 2, I'm gonna get a +1/2. When I plug in 3, I'm gonna get a -1/3, and then a +1/4, a -1/5, +1/6, and then it just kind of keeps going, okay? So in just looking at the first few terms, what do you think is going to happen with this series? Is it going to converge or is it going to diverge?
Diverge.
And tell me why.
Because the 1 over n, if we keep adding numbers, it's just going to keep getting smaller and smaller and smaller and smaller and smaller. It's never going to reach to a 0 because it's negative and positive. It's like it rotates. It goes from positive to negative, so it won't get like to 0. So it won't. I feel like it can't converge.
Okay, so we have a diverge thought. Anybody else have another thought?
It's bounded above and below.
Okay, but how does that translate to its convergence or divergence?
It doesn't really approach anything, so it doesn't converge. It just keeps going on and exchanging between above and below 0. So it'll be diverge.
Okay, so we've got 2 votes for diverge.
Converged.
Could it converge since it's
Converged.
Okay, so we've got 2 for converged. Can I get at least one of you to, I get 3 for converge. Can I get one of you folks to maybe explain your reasoning here?
Would it be diverging because it's not a decreasing sequence?
Okay. Well, I want to hear from the folks who maybe think that it's converging.
I'm going to say converging because you're going to continually add numbers until you get so close to 0 that those numbers that you're adding is going to be, it's not really going to affect your number. So you're going to be able to say that you can reach a sum.
But what about the negative? It gets further away from 0.
It's still getting close to 0.
You're right.
I said it's converged.
It's like a sine graph that's like going up and down, but the amplitude between the 0 line is just getting smaller.
Okay. You're right. But it doesn't get to 0 though, ever.
It won't because it's a series.
Yeah, you're right.
All right, so let's kind of use this visual a little bit here. So I'm going to plot a few of these points. So the bottom green point is -1. The top one is 1/2. Then it's at -1/3, and then +1/4, and then -1/5, then +1/6. Right? Yeah, exactly. So what we're seeing here is, I think it's easy to be distracted by the positive negative signs, but the bigger question about convergence is, are we getting at the end to a place where we're barely adding anything? In fact, we're adding something, it doesn't matter that it doesn't get to 0, but we're adding something that's so close to 0 that it's really negligible. Okay, so sort of visually, this is what we're looking at. But let's apply our alternating series test. So the first thing we're going to do is we're going to take the limit as n approaches infinity, but only of the pink part, only the 1 over n. So we're saying the limit as n approaches infinity of only the b sub n. Now, when I plug in infinity over here, I sure do get 0 out. That's the first thing we're looking for. As we go to infinity, do the n terms get close to 0? And our answer is yes, they do. Okay. Now, since we found that the first step is 0, now we go on to the second step. Is b sub n, just the 1 over n part, a decreasing sequence? Yeah, right? So that means we want to compare 1 over n to 1 over n plus 1. And we've done these kind of comparisons quite a bit. I feel very confident that we all can see that 1 over n is larger than 1 over n plus 1, which means that it is decreasing. So as long as both of these are true, then your alternating series converges. Does that make sense?
Professor, why did you choose 1 over n plus 1?
Because if it's a decreasing sequence, one term, the one that comes before, has to be greater than the one after it.
Oh, okay.
Okay. So like we say n is like whatever term we're talking about. N plus 1 is the next term. And then if we plug in n minus 1, that's like the previous term. All right. Other questions about this alternating series test?
So did you write the n plus 1 with the intention of proving that it was decreasing?
Yes.
Okay. Thank you.
So 1 over n represents some term, and 1 over n plus 1 is just the next term in our series. So if some term is always bigger than the next term, then it's going to be decreasing. It might be helpful for us to think about the decreasing as like a sub n has to be greater than a sub n plus 1. So all I did was plug n into the equation and n plus 1 into the equation. Okay, let's take a look at example number 8. So I know we're in the alternating section, but we would also recognize that it's alternating if we see this part, right? The part in the yellow is the part that means, ooh, we have an alternating series. So what does that make our b sub n in example number 8?
N squared over n squared plus 5.
Good, so it's this whole thing, right? That whole part is our b sub n. Okay, so if we wanted to apply our alternating series test, we're going to first see what the limit of just the b sub n part is. Okay. And so when we plug in infinity here, we're going to get an indeterminate form, and then we could use L'Hopital. Or we could look at n behavior in general and notice that the degree on the top and the bottom are the same. And so we could shortcut it. And what would this series, or what would this a sub n converge to?
1.
Converge to 1, right? Because that's a 1n squared over a 1n squared. Now 1 is not equal to 0. Okay. So that means we can stop right here because it diverges. So the first part is important because if the first part's true, then you can try the second part. But if the first part's not true, then it's not going to converge. It's going to diverge. All right. Why don't you guys try example 9 and 10, okay? So see which parts are the b sub n, which parts make it alternating, and then see if you can figure out if it converges or diverges. Now, I know in example 9 and 10, we've got this -1, but it doesn't say n plus 1, it's n minus 1. But that's also another way, maybe a little bit less common, but another way of saying, hey, you got an alternating series, okay? Anytime you're raising -1 to a power, if it's even, it's going to be positive, but if it's odd, it's going to be negative. That's where the alternating comes from. All right, so in both examples 9 and 10, the thing in the yellow, even though it doesn't look exactly like the formulas we saw above, those are the pieces that make it alternating. What is our b sub n in example number 1?
1/7 plus 2n.
Beautiful. I'm so glad that you didn't just say 7 plus 2n, right? We want to be really careful here that 7 plus 2n is in the denominator. What is our b sub n for number 10?
2n/4n.
Good. All right. So I'm going to start both of them the same way. We're going to take the limit as n approaches infinity. And we're going to do the same thing down here. And what do we get for example 9 when we find the limit as n approaches infinity?
0.
We're going to get 0, exactly. And so that means that we can continue on to the second step, right? What about in example 10?
2/4. 1/2.
Now we're going to get 1/2. That means we can stop right here because this diverges, okay? 1/2 is not 0, so it diverges, right? So let's go back to example number 9 and see what, if we can figure out if it's decreasing or not. And so if it's decreasing, and let me do this off to the side just so we have a little bit more room. If it's decreasing, that means that a sub n is greater than a sub n plus 1. That some term is bigger than the one that comes after it. So how do we write a sub n in this particular series?
1/7 plus 2n.
1/7 plus 2n. How do we write a sub n plus 1?
1/8 plus 2n. Oh no.
9 plus 2n.
Plus 1.
Tell me before you simplified it. Like literally, what did you plug in?
7 plus parenthesis n plus 1 close parenthesis.
Yeah. Okay. So that's where we're in the previous problem. I was getting that n plus 1 from. There was just one place to plug in n, but in this case, I have to put it like I have to multiply the 2 by it, and then I have to add 7. Okay. So you can simplify this if you want, or I think you can also tell from here that there's just more going on in the denominator. So the second one, this has a larger denominator.
What's smaller?
Which means that it's smaller, which means that it's decreasing. So this converges. All right. Does that maybe clarify where I was getting the n and the n plus 1 from the previous example?
Yeah.
Okay, good. Sorry, I skipped that step. Okay. So we've got in another example, one that converges, one that diverges, all right? And we've seen that -1 to the n minus 1 is an alternate way of saying, hey, we've got an alternating series here. So in our last two examples, we're going to take a look at some other less common ways of saying, hey, you got an alternating series. Right? So it's not that anytime you see a -1, it means it's alternating. But if you have -1 raised to a power, and that power changes from even to odd to even to odd to even to odd, That's the part that makes it alternating. So even though this randomly says n plus 6, it really means the same thing as like n plus 1 or n minus 1. It means this is alternating, and the n over n squared plus 9 is our b sub n. Okay. So let's find the limit as n approaches infinity of our b sub n. What's that going to go to?
Pi over pi. I mean, pi. Infinity over infinity. Sorry, my head's somewhere else.
Infinity over infinity. Okay, but we need to keep going there.
Well, 0.
Okay, so we're eventually going to get like 1 over 2n if we do L'Hopital's, which will give us 0. Or we can say the power on the bottom overpowers the top power. So we know that the end behavior is a horizontal asymptote at y equals 0. Okay. So when we have this, again, we could use L'Hopital's, or you can say that you are comparing the powers between the top and bottom, and you know that that end behavior goes to 0. All right. So this is a good start. This means we can continue on to the second step. And if we want to find out whether or not this is decreasing, if we try our regular way of saying like a sub n and compare it to a sub n plus 1, we would get n over n squared plus 9. And then over here, we get n plus 1 over n plus 1 squared plus 9. Right? So what do we think is happening here? What's the relationship between an a sub n and an a sub n plus 1?
A sub n is larger
How do you know that?
because it's a smaller denominator.
It's kind of hard to tell because of the plus 1 on the top.
Yeah, I would say yes, the denominator is larger, but we have a plus 1 on the top as well. So it's not so cut and dry, okay? So in the situations where maybe it's not so cut and dry, what you can always try is you can try finding your first derivative of your b sub n. Because if you find your first derivative and you find the critical points, and then you test in between those critical points. Anytime your f prime is negative, that means that you're going to have a decreasing function. So a negative f prime means it's a decreasing function. Okay? Now, if we were to take this derivative of n over n squared plus 9, we'd have to use our quotient rule. And what it would give us is something that looks like 9 minus n squared over our denominator squared. Okay, so I just got this using the quotient rule to find the derivative. Now, the numbers that make this 0 are going to be 3 and negative 3. Okay. But because I'm looking at an infinite series, I don't care about that negative 3. I really just want to know what's happening before and after 3. Okay. And it turns out that before 3, this function is actually increasing because the first derivative is positive. But after that, it starts to decrease. So in the long term, the bigger denominator, because we're squaring it, overpowers that plus 1 on the top. Okay. But before 3, like the first few terms are actually going to look like they're increasing, because the function does go up a tiny bit and then it starts to decrease. But what we're concerned about is exactly this part, the end part. If the end part is decreasing, that's good enough to say we've got this limit approaches 0, we've got a decreasing function, and therefore this series converges. Okay. So I know that's a little bit of a throwback to Calc 1, but just thinking like, why did we learn about all these derivatives and like how do they help us? And don't forget that that first derivative always tells you about whether the function is increasing or decreasing, right? Because the only way to get a positive slope is if your function is going up in value. And the only way to get a negative slope is if your function's going down in value. So it's sort of another use for those derivatives to kind of see like, okay, how can I confirm for sure that this is decreasing?
Quick question.
Yes, sir.
So for your, when you take the derivative test, even though n starts at 1, we're only worried about just the end behavior. If the end behavior is continually decreasing, then it's okay. Then this test will go ahead and prove that it converges.
Yes.
Okay.
All right. So we've got one last example here. All right. And this one I wanted to show us because it's a little bit of like a hidden situation, because at first glance, this does not look like it's alternating. There's no -1 to the power of something. So at first I might be like, well, this is not alternating. I can't use the alternating test, but it is alternating. What part of this tells us that it's alternating?
Cosine.
Okay, now let's just be clear here. It's not just the cosine, okay? But more significantly, it's that cosine, we're only looking at values of pi, 2 pi, 3 pi, 4 pi, 5 pi. So if you only look at the pi values of cosine, those go between +1 and -1, +1 and -1. All right, so in this case, the cosine of the n pi, that's the part that tells us, hey, this is alternating. Now, it's not as common to see it this way, but I did want to kind of show us, like, there are other ways of saying that things alternate. But at the same time, that doesn't mean that every time we see a cosine, it's alternating. Okay, so we need to be a little bit careful about what assumptions we're making. Now, in this case, my b sub n is not going to be the square root of n, but rather b sub n is going to be 1 over the square root of n, right? For the same reason that Mariah said earlier that we had like a 1 over 7 plus 2n. If it's in the denominator, it has to stay in the denominator. And so let's go ahead and do the first part of the alternating series test. And when we substitute in infinity over here, the denominator is going to overpower the numerator. So we'll get a 0. That means we can continue on to this. What happens if we compare a sub n to a sub n plus 1? So a sub n would be 1 over the square root of n. How would I write a sub n plus 1?
N to the negative. Oh,
What's that?
I was gonna rewrite it differently, but 1 over the square root of n plus 1.
Yeah. Okay. So which one is bigger?
A sub n.
Left.
Yeah, the one on the left is bigger. That means that we've got a decreasing function or series. So altogether, this one converges. All right. So the alternating series, not necessarily super challenging, okay? We're taking pieces of things that we already knew and just applying it to a situation where maybe the points, if you think about them, are both above and below the x-axis, but they ultimately, the question is, are they getting closer to 0? That would be the first part of the test. And then are they always decreasing, meaning the numbers are getting smaller and smaller and smaller, which means they're getting closer and closer to 0. All right. So that's it for today's lesson, all right? And that'll take us through the end of the content that is on tomorrow's exam. Does anyone have any questions about the alternating series before I stop sharing my screen?
Yeah, on example 11, to find the critical points of f prime x, you just use the quotient rule for the b of n. And that gives you 9 minus x squared. And then we get 3.
Because critical points are when the first derivative equals 0.
Okay.
Okay, so the only way we could get 0 out of there is if x equals 3 or negative 3.
Right. All right, cool. Thank you.
Right. Any other questions on 11.4? Yes, I will post the key for quiz 13 before the exam, so you should have access to that before the exam. I know that it's summer school, we're moving so quickly, and I know that we're learning a lot of like new content, so I will post that so you can take a look at that. Okay. For my answer key though, I will tell you for some of the questions where I say, hey, use 2 tests, I used 1 test and then I showed the work for that 1 test and then I just wrote out like, these are the other tests you could choose from, but I didn't do the other test. Okay. So it does have at least 1 worked out test per question, if that makes sense. Okay.
As long as I could check my B sub n.
For
the quiz. I just want to make sure that my B sub n's were correct because I had that same question whether or not you were going to post the key.
Yeah. I think it's the only fair and kind thing to do, especially in a summer school pacing class. All right.
Thank you.
Well, if there are no